In this video, we're going to look at several kinds of problems that we're going to encounter in Chapter 6. Alright, so first of all, I want to talk about some key terms or some vocabulary that you're going to hear me talking about. First one is Avogadro's number. This is telling me the number of things that there are in a mole of a substance, and that number is 6.022 times 10 to the 23rd. It's telling me how many things if I have 1 mole. So if I have a mole of hair, I'd have 6.022 times 10 to the 23rd pieces of hair. If I had a mole of shoes, then I would have 6.022 times 10 to the 23rd shoes. So just like a dozen means 12, a mole means 6.022 times 10 to the 23rd. Molar mass, this is telling me the mass of 1 mole. A mole ratio is a ratio between the coefficients in a balanced chemical equation. And by coefficients, I mean those numbers out in front. And then finally, a limiting reactant is a reactant, one of our starting materials, that limits the amount of product that I can produce. In my first equation, I'm going to just practice balancing a chemical equation. So I like to start out and make a list of the elements that I have. And I have to have the same elements on each side. So I have 1 carbon, 4 H's, and 2 O's. So here's the 2 O's, the 4 H's. On the other side I have 1 carbon, I have 2 H's, and I have a total of 3 O's. Now to obey the law of conservation of mass, I have to have the same number of each atom on both sides, and I do not. I have 1 carbon here and 1 here. Those are balanced. I have 4 H's but only 2. So in order to balance it, I have to put a number out in front that's going to balance it, and that's a coefficient. So 2 times 2 gets me 4 H's. That also changes my number of O's. So 2 O's here plus the 2 here gives me a total of 4. Now on this side I have 2 O's, on this side I have 4. So I'm going to have to put a 2 here because 2 times 2 would get this side 4. So now I have the same number of each kind of atom on both sides, and that's going to tell me that it's balanced. Okay, the next example is using a polyatomic ion. And I can do these the same way, except I'm going to make my life a little easier, and I'm going to leave those polyatomic ions together. So I have 3 NAs, I have 1 PO4, I have 1 Mg and 2 Cl. So in splitting the PO4, instead of splitting it into 1 P and then 4 O's, I'm going to leave it together. On the other side, I'm going to have 1 Na, I'm going to have 1 Cl, I have 3 Mgs, and I have 2 of these PO4s. And you can see that none of those are balanced. So I'm going to start, it doesn't matter where, maybe I'm going to start with my sodiums. So I have 3 on this side and only 1 here. So I'm going to try a 3. So that would give me 3 sodiums, and that's going to give me 3 chlorines. So now my sodiums are balanced. I'm going to move on to my P's. So I have 2 P's on this side and only 1 on this side. So I'm going to put a 2 out in front. So now that gives me 2 P's, but that also gives me 2 times 3 is 6 sodiums. And now my sodiums are off. Well, that's okay. It just means I'm going to cross that one out, and I need 6. So I'm going to put a 6 here. So now I have 6 NAs. I also have 6 chlorines. So sometimes when you try it, it doesn't work. You have to cross it out and put something else, and that's fine. I have 1 Mg, and over here I have 3. So I'm going to have 3 on this side. So 3 Mgs. And now I have a total of 6 chlorines. So I have 6 NAs, I have 2 PO4s on each side, 3 Mgs, and 6 Cls. So that means my equation is balanced. Alright, the next one is I'm going to be using that Avogadro's number to convert between particles and moles. And that number, that 6.022, that always tells me the number of particles, and in this case it's molecules that I have, if I have 1 mole of anything. So I start out with the 1.75 moles that I was given. So I have 1.75 moles, and then I need moles on the bottom, so I put 1 mole on the bottom and Avogadro's number on the top. So I take 1.75 times Avogadro's number, and that would tell me the number of molecules. And I have 3 significant figures, so I have 3 significant figures. Okay, the next example that we're going to look at is how to convert from the moles of one particular element to moles of the whole compound. So I have 1.5 moles of aspirin. Now when I look at my formula, I have 9 carbons, 8 hydrogens, and 4 oxygens. And they're asking me about carbon. So I could say that there are 9 moles of carbon if I have 1 mole of the whole compound. So if I have 1.5 moles of the whole compound, I'm going to have 9 moles of carbon up on top, 1 mole of the whole compound on the bottom, and I'm going to take 1.5 times 9, and that's going to tell me how many moles of carbon. Now if I'd had hydrogens, then I would do 8 moles of hydrogen on the top. Okay, the next thing is we're going to be learning how to calculate the molar mass. And to calculate the molar mass, we're simply going to look up at the periodic table and find those average atomic masses. So for lithium, I have 2 lithiums, and then I would multiply by the mass, which is 6.941. And that's how I got the 13.9. For carbon, I would do 1 times the mass of carbon, 12. For oxygen, I'm going to do 3 times the mass of an oxygen, which is 15.9994. And that's how I got the 48. Then I simply add all those numbers up, and that's going to tell me how many grams if I have 1 mole of the Li2CO3. So now I'm going to be able to use this as a conversion factor to go between moles and grams of a substance. And that's exactly what we're going to do here. So here I have NaCl. So first thing I'm going to find the molar mass. So 1 times sodium's mass. And then 1 times chlorine's mass. I'm going to add those up, and I'm going to get 58.5 grams, and that's if I have 1 mole. So I start out with 737 grams. So if I start at 737, the grams need to be on the bottom to cancel. So 58.5 grams for 1 mole, and I would take 737 times 1 and divide by the 58.5. Since I started with 3 significant figures, I'm going to end with 3. And if I had moles and I was trying to go to grams, I would be doing the same thing, but I would have to switch that conversion factor around. Okay, my next one is I'm going to go and do a mole ratio. So now I'm going to be looking at the coefficients in my balanced equation. And I have C3H8, and they're asking me to find CO2. So in my balanced equation, there's a 1 here, and there's a 3 here. So that tells me that there are 3 moles of CO2 if I have 1 mole of the propane. So that's going to be my conversion factor. And I'm starting out with 2.25 moles of the C3H8. I need the C3H8 on the bottom, so 1 mole there, the 3 moles on the top. My moles would cancel, and I would take 2.25 times 3. And that's going to give me my moles of CO2. Okay, next we're going to try to put all this together. So we're going to be using our molar masses and our mole ratios. So I want to know grams of CO2, and I'm given grams of the C2H2. Alright, so the first thing I'm going to have to do is go from grams of the C2H2 to moles of the C2H2. And to do that, I'm going to need the molar mass. So I'm going to take 2 times carbon's mass on the table, 2 times hydrogen's mass on the table, and add them up. That's the 26 grams. And that goes on the bottom to cancel with what I started with the 54.6 grams. Now that's going to give me moles of the C2H2. Next step is I'm going to have to go from moles of that one to moles of the CO2. And to do that, I'm going to need that ratio of my coefficients, or that mole ratio. And my mole ratio says that I have 2 moles of C2H2 for every 4 moles of CO2. So here's my C2H2, so the 2 moles of C2H2 go on the bottom, the 4 moles of CO2 go on the top. And then I would cancel, and now I have moles of CO2. Well, they asked me to find grams of CO2, so now I'm going to have to go from moles of CO2 to grams of CO2. And to do that, I'm going to need the molar mass of CO2. So 1 carbon, 2 oxygens added up off the periodic table. That's 44 grams for each mole. and since I had moles here, the moles go on the bottom and those cancel, and I take 54.6 times 1 times 4 times 44, and I would be dividing by 26 times 2 times 1, and that gets me 185. So I was using my mole to mole ratio, and I was also using those molar masses. Okay, the next one is calculating percent yields. So it's going to take what I've done, but we're going to go one more step. And here's my chemical equation, and I've started with 50 grams of LiOH. So that's what I'm going to start with. And eventually I'm going to try to get to the LiHCO3. And this right here, this is telling me what my actual yield was. So this is if somebody actually did the experiment, what they got in the lab. So first thing, I have 50 grams. First step is to go from grams to moles using the molar mass. So I add up 1 Li, 1 O, 1 H off the table, and I get 24 grams. So 50 grams, 24 grams goes on the bottom to cancel, and I have moles of this. Next step is just like last time, do a mole to mole ratio. I have 1 LiCO3 and I have 1 LiOH. So 1 LiHCO3 for every 1 mole of LiOH. And I put the LiOH on the bottom so it cancels with this one. Next step is to go from moles of LiHCO3 to grams. So I'm going to need the molar mass again. This time 1 Li, 1 H, 1 C, 3 O's, all added up off the periodic table. And that's 68. And I put that on the top because I want the 1 mole on the bottom to cancel over here. And I take 50 times 1 times 1 times 68, divide by 24. And that tells me that I make 142 grams. Now this is my theoretical. So if I didn't lose any and everything was perfect, that's how much I should make. To find my percent yield, I have to take the actual yield divided by my theoretical yield. So the actual was given 72.8 divided by my theoretical, which is what I calculated. Take it times 100 to get a percent. And I started with 3 here, and the 72.8 has 3, so I get 3 in my percent. Okay, next topic is doing limiting reactants. So the limiting reactant is limiting the amount I can make. So the first step is I'm going to have to use what I started with, and I can't see it very well, but there was 70 grams of the SiO2 and 50 grams of carbon. So the first step is I got to figure out moles that I could make of CO, because it's asking me for how many grams of CO. So I'm going to take my 70 grams of SiO2, divide by the molar mass to get the moles. Then the next step is my mole to mole ratio, 2 COs for every 1 of SiO2. So 2 COs for every 1 of the SiO2. That's going to tell me how many moles of CO I could make. I'm going to do the same thing for my carbon. So 50 grams of carbon, divide by the mass for 1 carbon off the periodic table. And then now my ratio is 3 carbons and 2 COs. So 3 carbons and 2 COs. And the carbons are down here to cancel. So 50 times 1 times 2, divided by 12 times 3, that gets me moles of CO. Now between those two, this is the smaller amount. So that means this one is my limiting reactant. That's the one that I need to use to finish solving my problem. So I'm going to take that 2.23 moles of CO, and I'm going to have to convert it to grams using my molar mass of 1C and 1O, which is this 28 number. So 2.23 moles, the grams go on the top, moles on the bottom, multiply. That tells me this is the amount that I can make. I can't make any more than that because the SiO2 is limiting the amount I can make. Now our final problem is using heats in a chemical equation. So before we start, if we look at our equation, this is telling me for every 2 of the ammonia, because I'm talking about ammonia in this problem, I get 92.2 joules of heat, kilojoules of heat. So it's telling me I get 92.2 kilojoules if I have 2 moles of NH3. Alright, well first I have grams. I can't do anything unless I have moles. So once again, I'm going to take my grams, I'm going to divide by my molar mass, so 1 N, 3 H's. Grams go on the bottom to cancel, and now I have moles of NH3. Now I can use this new conversion factor, which says that out of this equation I get 92.2 kilojoules for every 2 moles. And the moles go on the bottom, so I can cancel with this moles. So I'm going to take 50 times 1 times negative 92.22, and then divide by the 17 times 2. And that tells me I'm going to get 136 kilojoules of heat produced from this reaction, if I start with 50 grams. If I started with something other than 50 grams, then I would put in the different amount here. So that kind of shows you the kind of problems that you're going to have in Chapter 6.